All right. Welcome, everybody, to the Playing Games Podcast, episode 18. And today I'm joined by researcher Michael Kuhn, or Michel Kuhn, I think. Michael, how are you doing today?
I'm great, thanks. Thanks for having me. I'm excited. Should I give a short
Uh,
introduction or?
yeah, maybe tell us a little bit on how you kind of came, or I'll specify it down, what kind of interested you to go down this route on this topic that we're going to go over today.
So first, I just give a short introduction. My name is Michel Kuhn. I'm a German PhD student at the University of Münster at the Institute of Physiology 2. It's the Wolfgang Linke lab, and everybody who is familiar with Wolfgang Linke knows that he's one of the world leading Titan researcher. So my research is about Titin and Titin associated proteins, especially when it comes to muscle contractions. And that's what I'm doing my research on, especially with the method of muscle X-ray diffraction, which probably most of you don't know what it is. But yeah, my background is in sports physiology, but I totally shifted away from exercise sports physiology more to basic research, so structure biology, molecular muscle physiology of sarcomeric proteins. Exactly.
Awesome. And that basically leads us into today's topic on a popular protein known as titin that many people are starting to give a lot of attention to, and even researchers as well. Um, so we could start off with maybe if you could explain what is titin, like what is this giant protein in the body or biggest protein in the body?
Yeah. So as you said, it's the largest protein in the body. Titin is one of the um, one of the filaments in the sarcomere. So we have myosin, actin, everybody's familiar with, but we also have titin. And titin spans half a sarcomere from the Z disc to the M line of a sarcomere, and it's also part of the thick filament. So it's interacting with the myosin filaments. So it's integrated into the thick filament, which are created by myosin, titin, and myosin binding protein C. And it's really important for the regulation, um, for the structure of a sarcomere, and for its adaptation. Especially when we talk about eccentric contractions, all the stuff, Titan plays a major role and is like a blueprint for the sarcomere because Titan really binds to or is connected to most of the proteins in the sarcomere. It can interact with actin, as I said, it's interacting with myosin, so it's necessary for eccentric, but also for concentric contraction. Most people don't know about this.
Yeah, and I kind of want to get into a little more on those things you said, go a little bit more in the details. But before we do that, do you know the history of Titan in the research on how it came to be, maybe how it was discovered, any of that, and then what brought it to be such a popular thing right now in the literature?
So it's really interesting because in so Titan was firstly known as connectin. It was I think uh, more it was new in the Asian research world, but also new in the Western world, and discovered more or less at the same time, right? So I think it was around 19 end of 1970, 80, where they start thinking about, oh, there must be like a third filament because Huxley and Huxley's theory about myosin actin uh, which was great, but they saw that there must be a third filament also involved, especially after stretch. So yeah, they started getting these gels too, Titan gels, really hard to make. So they're just a hand of people right now who can perform them correctly, but they saw there must be something else. And especially when the research developed more and more with mechanics work, so they looked at fiber mechanics, single fiber mechanics, looked more deeper into the sarcomere. Um, they did stretchings, so stretch experiments, for example, where you stretch a sarcomere. They saw like higher passive forces going on. And then, of course, researcher like Wolfgang Linke and other people in the mechanics world, there is, of course, Lieber, but also Wolfgang Herzog, which do a lot of Titan research. They got more and more into the Titan world. Exactly.
Awesome. And I again, some things that I do want to go back to on a couple of those researchers, because there does seem to be some sort of disagreement that I want to see if you can help clear up. But again, before that, to get a better understanding of Titan a little bit more, do you think you could explain its structure a little bit, like the different segments it has? It's You already kind of explained where it's located, but what does Titan have in it that can allow it to do so many different things?
Yeah. So Titan is an elastic protein. So like a spring, everybody says. It has IG domains. So, for example, the I band Titan, which is like the elastic part before it's interacting in the A band with the thick filaments. It's made up from IG domains. Then we have a really important N2A region, which is a signaling hub for mechanosensing. And then we have the PVK region, which is also, again, really important because there is where more or less the stiffness of Titan is made. So we have IG domains which unfold really easily with not much force. But when more force is applied with stretch, so passive force is applied on Titan with stretch, we see that the PVK region is stretched out more and more. And also this PVK region, the elastic part, can be changed or differs from isoform, from Titan to Titan isoform. And yeah, that's basically the key region, which is next to the N2A region, which is really important for adaptation of sarcomeres, of muscle fibers, and so on. Because maybe I have to say, we know that the more stiff Titan is, the more adaptation we get. If it's like longitudinal muscle growth or whatever, this depends on Titan stiffness and the N2A region.
And I mean, with the two regions of the IG domain and the PEVK region, I've heard one side say that the PEVK domains tend to be always more compliant in Titan always. However, there again seems to be some confusion on if the IG domain, the PVK is more compliant, but and like you said, the IG domains kind of stretch easier or unfold easier, or I think they stretch easier and unfold at higher forces. Maybe we can elaborate a little bit more on that, depending on like the task that's being put on the muscle, if it matters whether it's active or if it's passively lengthening.
Yeah. So this is a little bit more complex. So when we stretch a muscle, when we passively stretch a muscle, the IG domain definitely unfolds faster. or before the PVK region, right? And the stiffness. So we first also have to mention that there is, of course, cardiac titin and there is a skeletal muscle titin. So cardiac titin has an N2B isoform, where skeletal muscle titin has an N2A. And we know that the N2B, so the cardiac titin isoform, is stiffer than the N2A region, than the N2A skeletal muscle isoform. So this is one point. Another point, of course, seems like the fiber type where the titin is. So faster muscle have a more or have a stiffer titin isoform. So this depends on this, but titin shifts are quite, they can transform quite easily and fast. So depending on what you're doing, your titin's getting stiffer or more compliant. Yeah.
Okay. And then, well, speaking on that, then, when Titan is also known as an entropic spring with viscoelastic properties, do you think you could touch a little bit on what it's meant by it being an entropic spring? If it has to do with things with entropy, I believe, and then its viscoelastic properties as well. Where do those viscoelastic properties come from? Is it mostly from the IG domain?
Yeah. So of course the elastic properties, viscoelastic properties, as I said, it's quite complex here on Titan, because we have so many different regions which affect this. But maybe let me shift this talk a bit to to I mean, we are all interested into strength training, right?
Mm-hmm.
And I have to say this before, because then we just understand what Titan also does with stretch, and we understand the elastic and viscoelastic properties of Titan. So, as I said at the beginning, Titan is part of the thick filaments. And with stretch, we stretch Titan, right? And because Titan is connected to the thick filaments stretch also with stretch. So when we stretch a muscle fiber, the thick filaments, the myosins, are also stretching. And I hope everybody is familiar that the myosins have myosin heads, right? And the myosin heads are so the myosin heads can be in different positions. They can be closer to the thick filament backbone, so they are more in an off state, or they are closer to the thin filaments, which are more in an on state. So when we stretch a sarcomere, the myosin heads move closer to the thin filaments here. And this facilitates cross-bridge interaction, right? So Titin really primes with stretch the sarcomere for more force production. So, and this is what I want to say, because people are just looking, oh, Titin is getting stretched, right? There must be a mechanosensor effect. But to really understand Titin's function, we have to look at the whole sarcomere and how Titin affects not only the stretch, but it directly affects the outcomes of the contraction. So the concentric contraction, right? So it has, of course, this spring element effect, but it also has a priming effect directly on the myosin heads. And that's what we also showed or will be shown in further experiments in our research. So, of course, with stretch, Titin is getting stretched and has like a spring effect, but it is way more. Titin has way more effects than just this viscoelastic properties and the spring effect. That's what it makes way more variable.
So it seems to act differently between active and non-active contractions, like when we passively stretch it through maybe static stretching or immobilization, probably at a longer length.
Of course,
Um,
no. Yeah.
and then if we do something like an eccentric, and like you said, it also fluctuates or it also affects concentric contraction. Um, with an eccentric contraction versus just passively stretching a muscle, from what I understand, Titan gets stiffer, around like 3 to 6 times more stiff, if I remember correctly. Um, could you maybe elaborate a little bit on how it gets stiffer because of this, or like you said, it could have something to do with the
Yeah.
interference of the uh, active elements around it with it?
Yeah, sure. So why is getting Titan stiffer? So Titan seems to get stiffer with activation. So when calcium is present, it seems like Titan can bind via the PV close to the PVK region to the actin filament. And this is really interesting because when I mean when I hope everybody is familiar with, with the architecture of the sarcomere, when Titin at the I band binds to the actin, to the thin filaments, um, the whole spring, or at least the part behind the point where it binds to the thin filament, can get stretched more intensely, right? So we manipulate the Titin stiffness there at this point. So calcium causes Titin to bind to the thin filaments, and therefore it manipulates Titin stiffness. There's also another mechanism that can do this, and this is my research topic, and this is called the muscle anchoring repeat proteins, MAPs, and there are like 3 different MAPs: MAP1, MAP2, and MAP3. And MAP1 usually occurs in a healthy muscle just at really, really low concentrations. But we see a crazy upregulation in this MAP1 protein after eccentric contraction or after muscle damage. So in mice with some myopathies. And I showed in one of my paper, which I will submit soon, that MAP, and this is also has been shown by other groups too, but I showed the structural evidence that MAP binds the N2A region of Titin to the actin filament, therefore increases Titin stiffness and causes this transition of the myosin heads closer to the thin filaments in the A band. So this seems to be first a mechanism to, increase force production, but it also seems to be a mechanism to prevent further muscle damage. And it really just seems to occur after eccentric contractions or after eccentric training. So therefore, these are the 2 mechanisms until now that can stiffen up the Titin: activation with calcium and interaction with the MAP1 protein.
So it's not just calcium alone that can cause this stiffness. In terms of calcium and Titin, how concrete is the evidence with some things with calcium happening? Because I know maybe a couple years ago it was kind of more so concluded that calcium has an important role And then over time, it kind of like went back down to saying, well, there might be something else happening. Maybe we're not as sure as we thought.
Yeah.
So where are we right now in terms of, calcium's important role with Titin?
So there is still a lot of debate going on. So a few really important researchers, they don't buy into this. There is, for example, from Kisa. She has the winding filament theory, right? Are you familiar with this theory? That the that basically because of calcium, Titan winds around the thin filaments and stiffen up.
That's
Yeah,
that's the winding filament theory you said,
yeah,
right?
yeah.
Yeah.
And this is what a lot of people don't really buy into it. I think there is quite some evidence that showed that there is an interaction between Titan and the thin filaments. So, and this causes Titan, increase in Titan stiffness. What I definitely believe, also because I just trust my work, is that MAP binds, right? And that this has definitely an effect. So at least it doesn't matter what, but Titan is able to bind to the thin filaments.
Mhm.
Usually, I mean, it has never been really shown in humans. I mean, at least direct binding. But I mean, most of our research is in mice, in mammals, which is really close to humans. And yeah, also I've got human data that shows that there is an effect of MAP1 and Titan on structural on sarcomeric structure. So I'm quite sure.
Good, awesome. Now, one thing that I'm interested in as well is how you said Titan, helps with eccentric contractions, and people uh, have jumped to say, well, we are stronger in eccentric contractions because of this extra Titan filament. Now, this is where I get a little skeptical because I'm curious if any data ever showed forces measured in Titan that come close to the forces measured in muscle, at least from a whole muscle level. Um, and I think this is where kind of Lieber kicks in and he goes, well, at the single fiber level, Titan is the bearer. But if we talk about whole muscle level, he argues that the extracellular matrix bears more passive load. Um, so I don't know if maybe you agree with that, or maybe you think Titan bears more load than um, researchers like Lieber kind of downsize it a little bit.
So the problem is, and this is the big problem in muscle physiology, is like um the the transfer of knowledge to a different level. So I personally study on muscle fibers. There's also myofiber. Yeah, you can also do the research on a myofiber or on a whole muscle level. Why am I studying? I study Titan in skinned muscle fibers because we incubate these fibers with different drugs, for example, or solutions. And this is why you need permeabilized fibers for this. I'm using X-ray diffraction, the method. So we shoot really high intense X-rays through muscle fibers. They diffract. So I'm working on synchrotrons, and that's why we do this at this level. Of course, there might be changes um, when we look at the whole muscle level, right? But I think, to be honest, that and does it really matter at the end? Of course, we have the extracellular matrix, but what's happening inside a muscle will always be the same inside the sarcomere, right? So, and we see this when we actively manipulate in a muscle fiber titin, because um, uh, we have a paper out at PNAS where we cut titin with a virus, with a tobacco edge virus, and we can cut titin by 50%, and we see force drops. We see this and this quite direct. So maybe you have the chance to put in the paper to just link it in there. And I know that Lieber has an opinion on Titan and the extracellular metrics, but in my opinion, if you break it down to the level, there is not much difference. There's not much difference, and the trend will be the same. This is what we also see in most of our studies. When we look at the myofiber on the on the myofilament, on the fiber, or on the whole muscle level, the trends are quite similar. Yeah.
Mm. Yeah, and I mean, there are also some studies with immobilization where I think they injected cow pains on Titan, and they saw Titan degrade or anything like that, and then they saw reduction in passive tension, um, and then some have been using that as showing evidence that Titan bears passive tension. But again, I'm always skeptical, and I always say, well, how was intramuscular, how was intramuscular collagen, water, and all of that stuff.
It definitely has an effect. It definitely has an effect. But again, also in the whole muscle, the whole muscle consists of 100,000 million of sarcomeres, right? And there must be a force production. There must be the force transmission. And we know that Titan is really important for all this because it's organizing sarcomere structure. So force, lateral force transmission, longitudinal force transmission, it's really important. It's really important. And we can really see this. Have a look on our study design, pre-post, by cut and Titan, how this affect lattice spacing, how this affect myosin heads, how this affect all different sarcomeric proteins. And I mean, this is evidence how really important Titan is in the sarcomere. So it doesn't matter if you have a look at the fiber or the whole muscle level. Muscle produce force in the sarcomere, and this is also a point. I'm looking right now because I'm familiar with integrins and that everybody looks and the hype of integrins and extracellular metrics. And I totally agree. There will be signaling pathways, but nobody really studies the most important motor proteins. Where force production, where is the deformation comes from? Yeah, it comes from longitudinal, from titin. It comes from myosin and actin. And the funny part is, I'm really good with Martino Franchi. We will do in future some big collabs. And when I was a bachelor student, I went to Martino where he did a lecture, and I talked to him. Everybody looks at mTOR signaling pathways, right? And all integrants and all other stuff. And because it's interesting, there is not much evidence when we look at Titan and mTOR activation, right?
Yeah, I don't think there's been any convincing link with mTOR and Titan, right?
Because you don't need it. Because I'm looking at MAPS, and MAPS seems to shuttle directly to the nucleus and introducing hypertrophy program. This is also what we can see in a study by Robert van der Pil, where they do diaphragma de-innervation. And what they can see basically when they stretch one side more by de-innervating the other side, we see, and also there are studies from this group where they actively manipulate Titan stiffness. So when they actively manipulate Titan stiffness in a mouse model, we see more longitudinal hypertrophy. We see more radial hypertrophy. Because Titan not only causing longitudinal hypertrophy, Titan stiffness, it seems like it also causing the muscle to do addition of sarcomeres in parallel, because this is also a mechanism to downregulate the tension of the sarcomere. You can, of course, do sarcomerogenesis, but you also can do just increase the number of sarcomeres in parallel.
So yeah, because I mean, the reviews that I've read is that they seem to be more convinced that Titin does cause an increase in serial sarcomere number, or this sarcomerogenesis, more, or at least more evidence for that than sarcomere causing parallel addition or hypertrophy in that case. And again, the reason they gave is that, well, we haven't really seen any, convincing link between mTOR and Titin. But I mean, with what you said, like you said, we probably don't even need it, right? Because it kind of directly affects it in its own way.
Yeah.
Right?
I mean, it totally, and this is again what I was talking a lot with Martino. And he seems slowly to buy into this after several years. Signaling pathways seems to be different for sarcomerogenesis and hypertrophy. So increase in cross-section area. Why should they be the same?
Well, with them being different, I mean, there is research showing that we can lose sarcomeres in parallel and gain sarcomeres in series through immobilization studies. But can there be cases where both of them could also occur together? Sarcomere number and parallel sarcomere number, like you said, because they're both ways to reduce the tension in the muscle, right?
Yeah.
So even though they have different pathways, does that mean they can never occur simultaneously in certain
No, they're just, I think they're independent. Why would nature just, I mean, I mean, this is like, I mean, right, we're still looking for, well, we seem to look for one mechanosensor. I mean, one mechanosensor, we know this is Titin. Titin is it's definitely a mechanosensor, right? And just I know the paper from Henning Wackerhagen from Munich, and I totally disagree. Where he states he has a paper what mechanosensors are for hypertrophy with Brad Schoenfeld. I totally disagree on this point with him, and where he says like Titin has no effect on hypertrophy. That's just I totally disagree on this. But I mean, we have some data. We will get some more data, and then we will see what's happening. I can't talk about this because it's a new mouse line basically.
Mm-hmm. I mean, I definitely think they're. I mean, I'm more on the convinced side that it does signal serial sarcomere number and parallel sarcomere number, like you said. And I guess my point is too that, I mean, those two additions of sarcomeres in series and in parallel, there are situations where they can occur together, right? Like in maybe eccentric contractions or resistance
Sure,
training, right? Where
sure.
right?
Yeah,
Or
they definitely can occur at the same time. I mean, just look at puberty. People growth. I mean, they have longitudinal growth of their sarcomeres because I mean their bones are growing, body height is growing, and they pack also on some cross section area. Definitely, so it definitely goes at the same time. I'm just saying like there might be, and I have, of course, I don't have no right evidence, but it just makes totally sense that there seems to be different pathways of the body for longitudinal muscle growth by activation of Titin, MAPS, whatever, Titin kinase, MRF, and then we have like, of course, different signaling pathways for cross section area, depending on the stimulus, of course.
Mhm. Yeah, I mean, with is there any evidence too for Titin improving force transmission through the sarcomere? Is there any like concrete evidence for that, or is that more so a theory or an assumption?
There will be soon. There will be soon. We're waiting for the acceptation.
Okay, I mean, excited to read that. I mean, I think it's an evolving field that I think is confusing too. I'm honestly confused because I hear it from both sides, and I know some researchers go in trying to push a theory that they walked in on. I guess to finish off, I kind of wanted to talk about a little bit of the contention going around with that there is no active passive dichotomy with Titan, where some researchers argue or contend that the force in Titan depends on the length of the sarcomeres and not the active or passive state, because Titan has different spring elements that have different properties.
Yeah.
And therefore, they argue that this internal structure of serially arranged springs with different properties explains everything that we observe in Titan. And so that's kind of what I gather from this side. And then we have the other side that kind of goes against that and say, well, we have very overwhelming evidence to suggest that there is this active passive dichotomy. So, I mean, maybe if you see the other side, or you think that the evidence is really clear that, Titan does act or gets different between active and passive contractions or passive lengthenings.
Yeah. So I think the first problem again is the methods people are using. Different labs using different models, methods. Some people looking at whole muscle, some people looking at muscle bundles, muscle fibers, single myofibrils. And especially in the field of muscle mechanics, where they measure forces, doing viscoelastic property tests, and all the stuff, there can be, there's a lot of confusion because nobody really can reproduce it in their way. They get different results. Then they said, when we activate, it looks different. When we do it in a relaxed muscle, it looks different. So it's really, really hard. I don't think there is like a really right or wrong. As I said, when we talk about the activation, we definitely see a change. We definitely, when we activate a muscle fiber, we definitely see that the force is increasing. Yeah. With stretch, for example, passive force increasing. This is definitely caused by a shift in Titan. Yeah. That's the only thing what I can really say here. I don't know what the other did. Even I'm connected to most of them. But I'm studying on the well, I just want to say what we study in this lab is really the basic research. So we are looking at what's really happening during the contraction, right? What's the baseline of Titan? What's with the molecule? What's happening? And all the human performance labs doing it on humans might be different. So
so there could be like this gap of people who study it from like the single fiber level to all the way back to the whole, or all the way to the whole muscle, and then as we get larger and larger, there can be these discrepancies of this
and
understanding.
that's the point. You have to think we work with really less confounding variables. We don't have ECM. We don't have whatever tendons anymore, right? But we are not interested in this because we look right now, we try to understand Titan in the sarcomere, what's the function, what's the use? How do cardiac or skeletal muscle drugs work on titin on the molecular base? And of course, the more you're going up to a whole muscle, to athletes, you have more and more confounding variables, which make it way harder. This is why I can't really agree with these people doing these big conclusions and say like Titan had nothing to do on a whole muscle level when you have that many confounding variables. Can you be really sure, are your methods really valid you use? Can you really isolate the effect? I mean, it's getting harder and harder. Yeah.
Yeah, I mean, I hope the research kind of begins to converge eventually, and we're able to bring all these things together. Uh, so that I guess that leads me to the last thing to finish off this very informative call. What are the futures, or what future do you see in your research here on how it could affect our understanding of Titan? I know you kind of touched on it a little bit. And from a practical standpoint, how can understanding Titan better from the fundamental level that you look at it um, really benefit this field, at least in the field that we're talking about? How could
Yeah.
understanding Titan better understand, or lead to better understandings of whole muscle?
Yeah.
Anything?
I mean, so of course Titan is, so I'm working especially in skeletal muscle, also in cardiac muscle. In cardiac muscle, Titan is a big player. So Titan is probably one of the most important filaments there. Most cardiac myopathies are based on mutations in Titan, or just having some problems with Titan. And I think the also skeletal muscle research has to focus in this field. And we start from now on, a generation, or in my age, a lot of research digging again into the Titan topic. And we see each year how more important Titan is. And as you said, we have to close the gap from myofilament level to the whole muscle level to understand the transfer of knowledge, of data, of force data, structural data, and so on. In the future, my field will be to have a look on how different drugs work on sarcomeric proteins like Titin, and how Titin affects all the other proteins, because this is the really important message I can give. Almost everything going on in the sarcomere is not just caused, but everything is interacting with Titan, whatever you're doing. And this makes it also so hard to really isolate the effects of thick filament, thin filaments, Titan, I mean myosin, actin, Titin, myosin binding protein C, desmin, everything on just one thing, because it's all these proteins are interconnected, but it seems like Titan gives all the structure. That's why it's one of the main players there. And there will be some changes must be made in some textbooks for sure. Yeah.
I mean, it honestly sounds like a very incredible machinery that the human body has, or I guess animals have too, I think. I mean, it's an incredible protein when I think of it, and it looks like it requires a lot of reading to understand it. So, I mean, if somebody's more interested in going deeper into understanding Titan, do you have any recommendations maybe where they could start?
Yeah, I mean, of course, there are some good papers of my supervisor, Professor Wolfgang Linke. He does also tons of reviews really to dig into the structure of Titin, what it does in skeletal muscle and cardiac muscle. Also, I'm sorry that I cut off your question on the viscoelastic behavior, but I can just suggest you one paper. I just looked it up again. It's called Unfolding of Titin Domains Explains the Viscoelastic Behavior of Skeletal Myofibrils. And because it's such a deep topic, it would take like 2 hours to talk about this, the viscoelastic properties of Titin. But everybody who is really interested into this, please have a look on these recommendations. There are like 2 big players in the field of Titin. That's Wolfgang Linke and Hank Granzier in Arizona, Bio5 Labs. So have a look at these papers. You will learn a lot, and I think, yeah, that will be definitely a big point in skeletal muscle research, also in exercise physiology. So I'm happy that more and more exercise physiologists, at least we are just 3 persons right now, from the exercise physiology in this field of muscle physiology, looking at structure. So it's just really a handful of people who are working in this field. But yeah, we try our best, and we try to get the strength training community more involved into these topics. It's always about money, you know. You don't get money for skeletal muscle research. It's the money is in cardiac land, but we try our best. Yeah.
Hopefully that changes over time. I'll make sure to link some of those important papers, down below if anyone's interested. Thank you again, Michael, for joining us. Do you know where people can find you, or do you offer any coaching services that anybody's looking to get stronger or improve their physique?
Yeah, sure. So my Instagram is muscle and strength performance. Yeah, I'm a powerlifting coach. Also bodybuilding, powerlifting and bodybuilding. So you can contact me there, of course, if you want to get stronger or whatever. Also, you can book consulting calls with me for any topics. So yeah, thank you very much for having me here.
I'll make sure to link your Instagram and maybe your website or your link tree, if anything, you have that down below. But thank you guys for listening, and see you guys on the next episode.